Thank you, Daniele. Thank you, Gerald, and the video and co-organizers for the opportunity to be here. I think you can see from my title that I've tried to maximize the overlap of my title with 3 of the 4 topics for this workshop. No prizes for guessing the topic that I've missed. Right. So I work in quantum field theory. I tell my Russian collaborators that dialectical materialism may be dead, but diagrammatic materialism is certainly not. I start with Feynman integrals. I don't choose them. God gave me the Feynman rules, and I look for diagrams that are difficult to calculate and then discover later what mathematics is relevant to that. So I start with the diagrams and discover mathematics. It's a lot more fun than other people who know pure mathematics and are desperately looking for some use for it. However, there is a fundamental element of fraud in my title. I have 2 topics, and the first of them will be indeed about resurgence, resonant resurgence, but there'll be no modularity. And the second topic is indeed about modularity, quasi-modularity, but I'm afraid there'll be no resurgence. So you see, I'm here to learn from you how maybe later I can put these together. So the first one, and this is work that I did with Michael Burinsky, prompted very much by the Isaac Newton workshop a couple of years ago, comes from a Dyson-Schwinger equation, and the whole point about it is this equation generates an infinite number of Feynman diagrams. I want to find an efficient way of calculating them, and I want to see what they add up to. I want to sum them. The second topic, this will be massless 6-dimensional phi cube theory. That's a theory in its critical dimension. It's got a dimensionless coupling constant. It's asymptotically free. And I shall be looking at an infinite class of Feynman diagrams, but of course only a very small subset of all the Feynman diagrams. This example of the type of very simple loop integrals that I should be doing, they're analytically simple, convolutorically become very complex, interesting. And the history of it is that as an exercise in the Hopf algebra of renormalization, one evening with to satisfy Dirk Kreimer and Anand Kong, I calculated 15 loops in an evening. It took several months to get up to 50 loops, and by the time I was giving data to Gerald, I think I had 500 loops. So this is something where you really are beginning to get very fine information about asymptotic behaviors. The massive bananas will be in 2 dimensions, and all of these internal lines will have mass unity, and there'll be an external momentum. And I studied these. Here, the algebraic geometry says there's an elliptic obstruction. You get elliptic integrals from it. I should be concentrating on this one, where the obstructions are a K3 surface. I once asked mathematicians what K3 stands for, and they said, oh, it was supposed to be the most difficult mountain to climb. It was even more difficult than Everest. Well, this is going to be rather easy. And I have additional material I probably won't get to that looks at the critical L values of automorphic forms going up to 22 loops. But I shall just stick here at 4 loops because this is already very interesting, not just with modularity, but with quasi-modularity. Okay, so that's the introduction. Now let's have a look. I've shown you what you're doing here. You're saying this self-energy is the 1-loop term, and then we put things inside and inside. And this self-energy is a 1-loop divergence there. The iterations of this will require renormalization. I shall use momentum space subtraction. I shall say that the self-energy vanishes at some particular value of the external momentum mu, so the inverse propagator, instead of being 1 over q squared, is 1 over q squared minus sigma, and I shall renormalize it so that the sigma vanishes at q squared equals mu squared, and at L loops, it will just be a polynomial in the logarithm. So it's a function of 2 variables, the coupling the square of the coupling constant, A, and a polynomial in this. And everything that I've done, the entire history of renormalization, is contained in this function of the coupling, the anomalous dimension. It's essentially the coefficient of log to the 1 at the renormalization point. Because if I know that, I can reconstruct the green function itself, which is given by this wonderful equation that the derivative of the propagator is the anomalous dimension evaluated as an effective charge that involves the self-energy itself. So I shan't be talking about this, I should just be talking about the asymptotic series for the anomalous dimension. Okay? So now the diagrams. I've gone to 4 loops because here you have what's called a rainbow diagram. And I can sum all of the rainbows, putting loops inside them. This is a series with a finite radius of convergence. The anomalous dimension satisfies a quartic equation. And it's a biquadratic, and it has that very nice thing. So we can expand this. And now, look here. I call this a renormalon chain. This is something that's going to grow factorially just from a single diagram is going to give you factorial growth through the process of renormalization. And I know how to sum this renormalon chain, just putting more and more things down there. It's Borel summable. It's got a wonderful, simple Borel transform. Here it's the Laplace transform, and the Borel function is just the function with poles at -1, -2, and -3 in the Borel plane. It's a perfectly well-defined integral. You can expand it perturbatively. It's a closed formula for the curve involving factorials that come from these poles. Yes. Yes, exactly. But it's rather nice to write it like this. And you see, of course, they have to agree at 1 and 2 loops, because there's no difference between a rainbow and a chain if I go to 2 loops. Here you see when I go to 3 loops, I have both a contribution from a rainbow and a chain, and I've drawn the interesting situation at 4 loops, and you can see that these integers are growing quite quickly. The process of renormalization, it's the iterative process of renormalization encoded by for the Hopf algebra of rooted trees. So this was the origin of interest when Kramer and Kohn were working on the Hopf algebra of renormalization. Now here is the non-perturbative answer to what this function is. It satisfies this 3rd order ordinary differential equation with quartic nonlinearity. Can you see there are 3rd derivatives and there are products of here. And that quartic is precisely the quartic that you saw in the inverse of the Borel transform, and the roots of those quartic are the rainbows, you see. So it's down here. And when I saw that, I had a lot of experience with Borel summation. I said, well, I can get a pretty good idea of how this function is behaving. It's a sign alternating series. So I can, all of the Borel singularities and the left half of the complex plane, I can close the contour. So my ansatz was that the solution to this equation, which is regular at the origin, is the Laplace transform of some Borel function, and I use the perturbative information on gamma to construct polynomials in the numerator and denominator. And when I do that, I need to work out what value of beta to put in there, and I did it experimentally to find what gave me the best answer. I didn't have any fancy theory. I'd done this 20 years before in different contexts. And I found that this worked rather well with beta equals 3. I thought that's quite nice, so that would correspond to factorial m plus gamma of m plus 3, factorial of m plus 2. So for instance, if I fit the first 29 terms in the perturbative expansion with a ratio of polynomials of degree 14, I found a pole at close to z equals -1, where the renormalon chain was. Bear in mind that I've got much more than just the renormalons, but the nearest singularity looked as if it was close to -1. The other poles were further to the left. And this method reproduces the first 15 decimal digits of G30. And so I'm pretty sure that I can calculate this function. Now, I was rather interested in this. I thought, well, it's a simple example in Borel-Riesz summation in a very well-behaved alternating situation. And then Gerald got hold of it and he said, well, David, you did a pretty good job, but I know the exact value of beta. And it's not beta equals 3. You were wrong by 3%. You should have had beta is equal to 35 over 12. You can imagine I was rather impressed by this and decided that I should find out where Gerald got it from. So this is the beginning of my education, but I'm assuming there may be some people here that have not played this game. I'm not taking advantage, so I'm going to give you a pedagogical introduction to it. Let's see how we're doing. Yeah, that's good. So now, first of all, what I'm going to do is make the progress to the interesting case, mathematically interesting case, of imaginary coupling. Remembering my expansion parameter is the square of the coupling. If that's an imaginary coupling constant, I've changed the sign of my expansion parameter, and I now have a sign constant series. And I don't know how to close the contour. And I should be interested in trans series down here. But there's an interesting historical argument. Freeman Dyson says we shouldn't expect expansions in the square of a coupling constant, even when we can resum them, because that would mean that the theory was defined for imaginary coupling constant, which would be a non-unitary theory. It's a bit ironic that there is actually two physics questions, I believe, in condensed matter physics that are related to the imaginary coupling constant theory. So phi cubed in 6 dimensions with an imaginary coupling constant theory is relevant, so I'm told, to percolation problems and the problem in condensed matter physics called the Yang-Lee edge singularity. And when I ask people, well, how come you have an imaginary coupling constant? They say, oh, you're allowed to have an anti-Hermitian Hamiltonian if you violate both parity and time reversal symmetry, but conserve PT symmetry. So this bit of benderology, I call it, Carl Bender, right? But don't ask me about the physics there because I'm out of my depth. Just take it for granted, this is the most beautiful way of writing my third order differential equation with quartic nonlinearity. I've cleaned it up into a form that looks really beautiful. And here's now, the x is now my expansion variable. Here's the constant term series. And I said, well, an is growing like a constant, which I shall call a Stokes constant, times gamma of n plus 3. And Gerald says, no, it's exactly 35 upon 12. And then he says, I can calculate the asymptotic expansion in 1 upon n, which are corrections to this factorial. And the first number is 97 over 48. So I said to myself, well, how did he do that, you know? And he said, oh, it's easy, David. You just look for linear perturbations about the perturbative solution, linear fluctuations about it. So instead of saying that seek a solution of the form, the perturbative solution you've got, and then something exponentially suppressed with e to the minus 1 upon x, I've normalized things so the first instanton has action 1, multiplied by some power of x, which was the beta that you thought was equal to 3 and isn't, times some function that's regular at x equals 0, and then there'll be nonlinear terms. And then put that into your differential equation and only keep terms linear in this parameter sigma, right? Well, that's easy. That will give you a linear, homogeneous, ordinary differential equation. Yeah? And it turns out that the only way of having a solution that's finite and regular at x equals 0 is if beta is equal to 35 upon 2. So I then say, yeah, I take out this e to the minus 1 upon x, I take out this x to the minus beta, I'm left with some function that's regular at the origin, I expand it about x equals 0, because I know its differential equation, and lo and behold, this small x coefficient of this instanton is telling me something about the corrections to the large n behavior. That's wonderful. So here now is my twiddles, just means some asymptotic series, which I would have to truncate when it starts to, when the next term exceeds the, when the ratio goes above unity. It's got some constant. It's got these, instead of expanding 1 upon n, I have progressively weaker and weaker gamma functions down here. And you can see I can now calculate this Stokes constant to any accuracy I like, because I just take lots of values of an at large n, and I calculate lots of values of bk at small k, and I invert a matrix. At which point Gerald will say, oh, no, use Richardson interpolation, but I shall show that that's absolutely hopeless for the problems I'm going to address later. So I can find this Stokes constant. Now, I call this resurgence in the sense of Jean Carl. He says, look, this, you found a perturbative solution, and that contains information about the instanton, or vice versa. Because it all comes from the same physics. In this particular case, it all comes from the same nonlinear differential equation, which is the area in which surely Carl's ideas are the most trustworthy and the easiest to understand. But then, talking to Michael Berry, he said, well, David, you've just done the first step in a process called hyperasymptotics, right? You found that the small value, B at small values of K, tell you about A at large values of N. And what about large values of B? Because when B gets large and grows factorial, it will start to do this, he said. So you want to find some C, right? I had a little rhyme about this, which I've forgotten. Large A's have little B's that tell them how to, I forget my little thing, and so ad infinitum. So the first step in this process is to realize, because it's a third order nonlinear ordinary differential equation, I would expect 3 instanton solutions. So I make exactly the same insats before. I take out e to the minus 1 upon x, and I find out the 3 instantons have actions 1, 2, and 3. I've already told you about H1 with this. And I make, find the linearized equations, and I find that the second instanton and the third instanton have to start at exactly x equals 5. In other words, not only are they suppressed by an extra power of e to the minus 1 upon x, but also at small x by the power of 5. So now I've got, my names for these is perturbative, first instanton, second instanton, third instanton. Okay. Now, here I want to show you, I think I'm on the right page, I've not skipped anything. Here I want to show you the form of the trans series just up to action 3. So here's the perturbative solution with action 0. Here's the first instanton. Here's the second instanton. It's got its own expansion parameter. It's a third order differential equation. And here's the third instanton down here. But of course, we can have terms involving sigma 1 squared, which has the same weight as sigma 2, or sigma 1, sigma 2, which has the same weight as sigma 3, or sigma 1 cubed. So there'll be new functions coming in here. And I find logarithms. At which point the expert sitting in front of me said, David, you were bound to find logarithms because you have resonance between your instantons. They're rationally related. Mine aren't just rationally related, they're as beautiful as they can be. They're at 1, 2, and 3. And I'll show you that these logarithms appear in a beautifully controlled way. So now you see, I'm in business. I just keep substituting this in the equation, and for these terms like F here, and D and E, no, D is the instanton, E and I, and so on and so forth, I have inhomogeneous linearized equations that involve everything I've done beforehand. And I'm rather good at writing computer algebra, and on my little laptop I can generate thousands of terms of all of these series and investigate the way that the asymptotic expansions of one occur in the Taylor expansions of the other. Now, notice here there's an element of ambiguity. Who says that my expansion parameter has to be sigma 2? I could add to sigma 2 any multiple of sigma 1 squared. So if you work that out, this means that the coefficient of x to the 5 in F is undetermined. It would just correspond to a shift in my parameters. And Gerald encountered this, and he said, well, what should I put it equal to? I think you put it equal to 0 because you couldn't think of anything to put it equal to. When Mishi and I did this calculation, we found that the whole series becomes massively simple. First of all, notice that the logarithms occur with this rather interesting rational number. We found out that our description of the trans-series, which I'll give to all orders later, works best if you choose that rational number for the fifth order. Notice it corresponds in some sense to a change of scale of the logarithm. If okay, so now I know what to expect. This is the large M behavior of the first instanton, and I expect it to involve the second instanton. It does, but I don't just find gamma functions. I found the derivative of a gamma function, which at large M behaves like a logarithm. So this is presumably associated with cuts in the Borel plane. And sitting underneath this psi function, which is a logarithm, is some constant. So now I found my second constant, but it's not, you see, this Firk-Stokes constant occurs here, but there's also down here, and it's quite a large constant. It corresponds, if you were to absorb it in a logarithm, it would correspond to being a very big shift. Okay, now comes the really interesting bit, because for the first time, I find what I call a backward-looking Stokes constant. In other words, instead of sort of looking in one direction in the Borel transform, I have to look behind me and in front of me. And in front of me is increasing action for me, and behind me is decreasing action. You've got this sort of picture. So now I look at the second instanton, and I find out that it involves a term with action 3 down here, and a term with action 1, the first instanton. And it's got this alternating sign, and there's no logarithm down here. Now, it's quite difficult to measure this constant, because if you look at it, it's only suppressed by a power of n to the 10 over 12, n to the minus 5 over 6. So you're expanding in 1 upon n, and they're mixed up in there. And later, there'll be logarithms around here. So I just use systematic matrix inversion. I don't try and adapt Richardson for purposes which she or he was never intended. So here I calculate these terms. I know exactly what I'm doing down here. If I want to find out the Stokes constant, I think Gerald had 4 correct digits of this, and I have 1,000. Okay. And there's a certain sort of simplicity in decoupling. So now I've got a forward Stokes constant and a backward Stokes constant. I've got a constant sitting under the logarithms of this. Then I find a constant sitting under the backward logarithms. So now this is something, this is the coefficient of, I think, sigma 1 squared. And it's looking forward to action 3 here and here. It's got a constant I've seen before sitting underneath the logarithm. And here, there's a fourth Stokes constant, constant in this logarithmic behavior with the backward ones. Now, at this point, I start to get scared, right? Is this going to go on forever? The calculations are becoming harder and harder to do. They're using up more computer time, more exploration. And I cut a very long story short. I'll show you the complete trans-series, the form of the trans-series, and its resurgence. This was discovered was conjectured to complete by the time I'd reached action 5. I had predictions for actions 6, 7, and 8, all of which turned out to be true to high accuracy. So there's a huge amount of information crammed onto this slide, and I want to go through it very slowly. So first of all, I've got an expansion here in the action, and I've taken out what would be just the contribution of the first instantons. And here I have 3 parameters. Sigma 1, some constant associated with the first instanton. It occurs to the power s, but s is just m minus 2i, where I is the power of the second instanton, minus 3j down here. And notice here that the x dependence is that I take out before I end up with something that's regular at the origin. Just I add a power of x to the 5. Now, where have these logarithms gone to? Well, they're all sitting in this amazingly cunning definition down here. This is a constant, And to this constant add this precise multiple of the square of the sigma 1 times log, and to sigma 3 add the same multiple of the cube of sigma 1, and all of the logarithms are absorbed in there. And I really don't know why, and it was my challenge to Mishi, who's much better at general proofs, to use the Aeolian calculus to explain this. And at present, it's just an empirical observation. It makes it extremely easy to calculate, because really, all I have down here is to work out what these numbers is. So at action M, made out of I instantons with action 2 and j instantons with action 3, and hence S instantons with action 0, calculate the Taylor expansions of these, go to large N, and find out how essentially this infinite dimensional matrix, but at large N, I expect to see the same numbers at small k. Yeah? And these are forward-looking. Can you see the total action have increased? But at the same time, you know, that the way the increase is being shuffled between the instantons, and here's now my forward Stokes constant with its logarithmic constant, and here's my backward Stokes constant. Took a long time to discover that this is the structure to all orders. And here there's a constant sitting underneath here. And then here I've got something that I haven't explained to you. Everything else is defined down here, I think, what this Q is. And this Q at large N is quadratic in log of N. So I'll show you what Q is. And Q, right, do you remember where I had things like this number times a logarithm? You take this number and it multiplies psi squared, and the second derivative for the logarithm of gamma function psi primed. And that's its leading behavior. And then think of this as being like log squared. And then sitting underneath, there's a coefficient of something which at large Z is log, and sitting underneath, that's the constant. And this number C1 is pretty close to the thing sitting under the logarithm. And this C2 is a big number, you can see. It's about 1,600. And I got rather excited, and I thought that it was close to C1 squared, but it turns out not to be. So that's the complete description of it. It's a third order resonant differential equation with quartic nonlinearity, whose, I would say, resurgence of the expansions of its trans series involves 17 terms. Think of that as being an infinite matrix, right, in which you have multi-indices of expanding at large N and multi-indices of things at small k, and there are sort of 17 different types of matrix element associated with it. And the 6 Stokes constants have been determined up to 1,000 digits, and I can find no. I'm pretty good at guessing the forms of numbers. I have a lot of track record for that, and believe me, if I can't find relationships between these and the usual suspects like gamma values, and there probably aren't any. Now, technically, it's quite demanding. I said I've got to take second derivatives of gamma functions. That means logs and log squares at large N, and suppressions by powers of 1 upon n, which are close to unity. So it's for this I used to discover the structure. Of course, once I got the structure, I could test it numerically. But to discover the structure, I had to use matrix inversion. And now comes my final thing. I think I've managed to stay more or less in time. Yeah, I'm about halfway. And that is that Mishi and I thought, well, we'll learn how to solve this difficult problem by inventing a simpler one that has resonance. So, yeah, that's what I want. So this was the way. This is an answer from quantum field theory. Right, this differential equation. There's a much simpler question you can ask about Yukawa theory, whose critical dimension is 4, and there you end up with a first order differential equation with only quadratic nonlinearity. It essentially says that g times this differential times g is some constant. And Mishy-Berinsky, Gerald Dunn, and what's your student mining? Yeah, his first name. Max. Max Meinig cleaned up on that. So we thought, and of course they had no logarithms, it's just one instanton. So what Mishy and I said, well, let's just ignore this term down here. Let's have a third order differential equation with quadratic linearity, with two instantons, and as sure as eggs, the two experts sitting in front of me had told me I would find logarithms. And they were completely wrong, right? That's a great advantage of being ignorant, that you don't, experts tell you, you find something out and you're very pleased, and the experts tell you that we knew that already, go and read the textbooks, and then you find something they didn't know, and they say, where did you get that from? And I say, well, just by being as ignorant and not reading the textbooks. Or just the textbooks. So I think the message is that, I think that the way that Gerald put it to me is, most mathematical proofs assume that things are in general place or something like that, and most physics things are as ungeneric as they possibly can be because they come from asking sensible physical questions rather than exploring the whole landscape of abstract mathematics. That's my epistemological answer. Okay, so now I'm halfway through. No modularity. Now I'm going to, and I shall restrict myself just to this diagram. I know nothing about it. I don't think this is an integrable system where clever people could find that. I can calculate, on the quantum field theory side, where I've got the Borel-summable case, I can calculate that anomalous dimension for arbitrary large coupling constants. But I can't tell you what the analytic form is. I can't do for it what you know I did using dual conformance with the ladders for phi cubed and so on and so forth. I don't have any sense that I'm looking at a perturbative expansion of a different question, a different expansion in 1 upon G. Mm-hmm. You need three constants at infinity, yes? I don't have those three constants at infinity. In other words, I don't know, right? If you go to some large coupling, right, and say, I'm now going to start to integrate this equation with the value, the first derivative and the second derivative, I don't know what combination of those corresponds to the thing that's well behaved at the origin, which is the answer to the perturbative question. Okay. So, I mean, it's a very interesting question, and maybe we should discuss it, but at present, I've not been exercised by that question. Maybe I should be. Right, let me talk about bananas. So now I'm in two space-time dimensions, and all my propagators will have unit mass, and there'll be an external momentum, so at most it's a process with one dimensionless ratio, the external momentum squared to the internal mass. And the reason why these diagrams are interesting is because of the algebraic geometry that comes from the Szymanczyk polynomials and the modularity that's manifest by the values, the periods of these diagrams. Here there's an elliptic obstruction, which was known since the 1960s and which I tackled in the 1980s and 90s. Laporta and I were the first people to look at this diagram. The algebraic geometrists say the obstruction is a K3 surface, and they're very interested. There's a lot of work recently on this one, which are Carbolau threefold. But I've investigated the generalization of modularity, the automorphic forms, the L series with David Roberts up to 22 loops. All I'm going to do is talk about this one, because it's already very interesting for me. So here it is as I give it to an algebraic geometer. She or he wants to look at some variety. It's a 3-loop integral, but the way I would do it, right, is introduce Schwinger parameters for each of these 4 lines and put one of them equal to unity. And this is the second semantic polynomial, and it's just the sum of the Schwinger parameters, one of which is equal to unity, times the sums of the reciprocals of the Schwinger parameters minus this kinematic variable. That's hopelessly inefficient as a way to calculate, but it's what people who like to blow things up do. You know the story of the algebraic geometer sitting on a plane discussing, and the steward gets worried because they're saying, well, we know we have to blow up this line, but do we have to blow up all these points as well, you see? So this is where Spencer Bloch tries to guess things about this by pure thought, or abstract nonsense, as he sometimes calls it. Whereas I'm actually interested in numbers. Now, for t less than 16, where this is real, notice when all of these x's are equal to 1, I get 4 times 4 minus t. So if t is less than 16, it's analytic function. It's got a branch cut corresponding to this particle with mass 4 or more decaying into 4 particles of mass 1. But for t less than 16, it's very easy to calculate numerically, because you go to configuration space. Not momentum space, where you have Schwinger parameters. Configuration space, it's a one-dimensional integral. You put that point at the origin of space-time, and you put that at distance x away in proper time, and you take the propagator for a massive particle in 2 dimensions, which is this Bessel function, with unit mass down there, and you take a Fourier transform with respect to the external momentum, which is another transform. This grows like, this falls off like e to the minus 4x. This grows like e to the square root of t times x. So providing the square root of t is less than 4, this is a well-defined integral. So it's very easy to do it numerically, and probably about 15 years ago, Stefano Laporta and I, together at a memorable conference in Bielefeld, discovered a formula for the on-shell value, because that's relevant to calculations like the magnetic moment of an electron. This is one of the numbers that we expected to encounter. And it's a stunning evaluation, because it's the product of gamma of 115, 215s, 415s, and 815s. Now, where on earth could that number come from? And when I show it to some mathematicians, they say, oh, you've discovered some hypergeometric function. Well, no, it's not. It's actually the square of an elliptic integral at the 15th singular value. Singular values of elliptic integrals occur when the elliptic integral at k over the elliptic integral at k primed is an algebraic number. And that happens with algebraic arguments, and it gives you elliptic integrals. And this is the square of an elliptic integral at the 15th singular value. Now, to prove this took 10 years of initially abstract nonsense and then eventually some analysis. So when Spencer looked at this, he said, David, I think that on general Grothendieck de linear conjectures, the ratio of the left-hand side to the right-hand side of your equation ought to be a rational number. They're pretty impressive, right, that these conjectures existed. Because this is the critical L value of a modular form of weight 3 and level 15. And then a little bit later he said, actually I can prove it's a rational number. And then in the final version of the paper they said, we've found some general argument in some old paper that no one had read before that says that this rational number is unity. Now, what I want is not twiddles and commutative diagrams. I want calculations. I want to be able to prove this using analysis that Euler and Gauss could understand. And here is where I get into quasi-modularity. So whilst these guys have an abstract proof, it was Dechat Samat who led the way here. And so the rest of my talk will be on modular parameterization with complex multiplication in q of the square root of minus 15, which is kind of implicated here. And the hero of the piece will be the Dedekind eta function, which we heard about abstractly. I think you call this I infinity in the previous talk, yes? Well, what I want, q, is some number, right? Complex number that corresponds to a particular point in the upper half complex plane. And that particular point in the upper half complex plane is defined by the kinematics of my Feynman diagram, right? And the wonderful thing about the Dedekind eta, it's got this q to the 1 upon 24, which tells you better take very special combinations if you want things to be well behaved at q equals 0, is that it's quadratically convergent, right? Q, first of all, will be small, but you don't just see powers of q to the n, you see powers of q to the n squared. So it's like a Jacobi theta function. It's fantastically, and you say, well, q might not be small, but I can always make it small because of this modular transformation. So it's periodic in Z, right? Z goes to Z plus 1. It gives me periodicity. I had to take it out, this q to the 24. And here now is the modular transformation. And the way to turn kinematics into a place in the upper half of the plane is to take judicious combinations of this Dedekind eta function. And here I tell you what they are. This is the map between a point in the complex plane. Eta n is just my abbreviation for eta of nz. So that will be an expansion in powers, not a q to the n, but q to the, not q to the k, but q to the nk. Mathematicians call this a Haupt module of gamma 0, 6. So I'm sure Jens immediately recognizes that. It's a modular function. It's got no modular weight, and it behaves, you can essentially turn z into minus 1 over 6z, and it's got a nice behavior. Of course, this is absolutely useless for a physicist, right? Because we start off, right, knowing what the external kinematic variable is, and we want to know where we are on the complex plane. And the mathematician says, oh, no, no, no. I can tell you how to get from the complex plane to your kinematics. I can't do it the other way around. But of course, we can do it because elliptic integrals. So in fact, to invert that relationship, all you need to do is to take the ratio of two elliptic integrals, each of which is given by an arithmetic geometric mean. Now this is an elliptic integral. Again, you see it's got weight 1, because eta has weight 1/2. It's got 4 on the top, 2 on the bottom, so it's a weight 1. And this is associated with the modular parameterization of an elliptic curve. And this quantity h down here is a weight 4 cos form of the congruence subgroup gamma 0 of 6. So these are the mathematical dramatis personae, and they reduce what looks like an extremely difficult third order inhomogeneous differential equation to simple algebra. Because this K3 surface that I told you down here is not some impossibly difficult mountain to climb. The Picard-Fuchs equation for the homogeneous third order differential equation associated with the algebraic geometry of the semantic polynomial is just is a symmetric square of the second order differential equation, which solves the elliptic problem for this one. There's a transformation of variables that says if you know the solution of that, you can transform your kinematics and the homogeneous solutions. So this psi squared, if I take psi squared, satisfies the homogeneous equation. And the modularity turns into this amazing third order differential equation. It just says the third derivative with respect to log q of what I'm interested over, evaluated at the appropriate point in the upper half plane by this Haupt module, divided by this right down here. Well, first of all, if it was homogeneous, this will be 0 because j is proportional to psi squared. The third order thing is this modular form. Now, thanks to my work with John Borwein, I know John and Peter Borwein, I know that how to expand this modular form. It is a sort of Eisenstein series of weight 4. You see n cubed up here. It's and so I can solve that. I can integrate that third order differential equation by pure algebra. I just expand this in powers of q. I know how to integrate a power of q. If I got q to the n, the integral with respect to log q is q to the n over n. And then I integrate it 3 times and divide by n cubed, which removes that n cubed. But also I've expanded in terms of 1 over q to the 6k, and that turns out down here. So what I end up with is starting with something that's not quite a modular form, because remember Eisenstein's theories need an extra constant, right? But starting up with something that morally is like G4, I've ended up with something with a 1 upon n cubed down here, which would correspond to modular weight minus 2, I think is what you would say. But for me, it's just a Lambert series. It's fantastically quick to calculate because my q will be small, providing I can jump around on the complex plane at will in the way that I could if I had modularity. And this is where my quasi-modularity comes in. But here's the result of the solution. I call this function h of z. I know you might say, well, I have 3 integration constants. I only got 1 integration constant, the value at q equals 0, which gives me t equals 0. I already knew it's a much simpler Feynman diagram. We remove the external leg down here. So I know that solution. By the way, this is enormously simpler than anything you'll find in Spencer's papers. So the problem of proving that result is the problem of what is h at the point in the complex plane that corresponds to the physicist version that t here is equal to 1 because we're on shell. And that's the point. It's 1 plus the square root of minus 5 upon 3 upon 2. So this combination of Lambert series has to evaluate to this multiple of pi. So the final proof is, where do Riemann zeta of 3 and pi cubed come from the properties of Lambert series? Now, I won't give you the proof of this down here, but I'll tell you the wonderful game that it led to. And of course, like most things, the formula with no proof is in Ramanujan's notebooks and lay there undiscovered for 50 years. So now I'm going to be a proper mathematician. I'm going to talk about pk of z, but it's really the same thing I was talking about, right? So I had an sk of q. I'm just putting q equals 2 pi iz. So think of this as a function, and it's periodic. And I'm interested in the transformation z goes to minus 1 upon z. But it's not got beautifully behaved modularity like the Eisenstein 4 or 6 that people like Oliver like. And it's not got just slightly wrong thing like Eisenstein 2. It's got lots and lots of corrections to modularity as k becomes bigger and bigger. And yes.
You can actually think of it as an iterative integral of a holomorphic.
Yes, exactly. Exactly.
K is even is an iterative integral of the generating series of the pi's of even.
Yes. Exactly so. And so I would say that I first encountered that equation down there, I can turn into an Eichler integral of that modular form. So you're exactly right. But what I want to do is to solve this by algebra, right? Because I'm quite good at computer algebra. So now, here, for odd k, right, so that corresponds to even negative weight, right? If I want to turn z into minus 1 upon z, I get z to the k minus 1. That would correspond to what you would call modular weight 1 minus k down here, and there's a correction. And somehow, Ramanujan knew what that correction was. Now, I can rationalize this, but where on earth did he get this? He said that the correction is, notice it involves powers of z here and here, z to the, it starts off with a 1 upon z, and then there's a z and a z cubed. There's an imaginary part that involves 2 pi I to the k. There's a real part, a real analytic function of z that involves zeta of k. So it's out of this formula we'll get the combinations of zetas and pi cubes that solve my banana problem, but also generate all sorts of other things.
If I can make a comment, Axel Kanschmidt and myself had a paper studying slightly more general version of this number series, and you can actually see as a sort of version of Cheshire resurgence of Gerald. So that series is actually asymptotic if you take k to be arbitrary.
Yeah.
And you can see the modular
okay.
as being the number.
So you're saying I'm looking at a terminating case.
Exactly.
Very good, very good. Right. Okay. So maybe you've solved the problem that I introduced at the beginning, that I didn't know how to combine modularity and resurgence. It's just that I was restricting myself to the weight which the Feynman diagram gave me. Okay. So now the proof of this is almost unobtainable, but there's some very nice expository papers. What I want to say is, how did this really surface? How did people know, apart from Bruce Bent, that there was this thing? Well, because this evaluation of zeta of 3, Ramanujan did publicize, and you see it's a very fast convergent evaluation of zeta of 3. The expansion parameter is e to the minus 2 pi, which is less than 1 over 535. You know, so if you want zeta 3, pi is supposed to come for free because there are fast algorithms for pi. Now, this is not the most efficient way of calculating zeta of 3 because there are stray isolated formulas from Chudnovsky and Borwein and Ramanujan for these things. But this is the beginning of an infinite family of odd zeta evaluations. This particular one only works for zeta of 4m minus 1. There's a different formula for zeta of 4m plus 1 down here. And I'm going to say, right, what I want to do now is to see if my Feynman diagram led me to something not only that I can prove using Ramanujan, but I can use to outperform Ramanujan to get faster convergence. And I'll show you that my Feynman diagram led me to a ratio of terms of e to the minus 12 pi over the square root of 15, which is where the complex multiplication comes into my title. Okay. So I think I really am doing all right for time, yeah? So here now is the result. Like most of my results, it was discovered empirically. This subscript of q means I'm taking q is equal to e to the minus pi times the square root of a, where a will be a rational number. So here I'm taking the square root of 3 upon 5, related to the point I was in the complex plane. And here now is the beginning of an infinite family of evaluations of zeta 3, which converges faster than Ramanujan. Because this term down here, as I said, goes like e to the minus 12 pi over the square root of 15, and these are higher order terms. Now, I discovered the formula for zeta 5 and zeta 7. Where do these rational numbers come from? Well, you should always look at the denominator of the rational factors. So when I went to zeta 5, zeta 7, zeta 9, I found an integer sequence, of which 605 is down here. It's really the coefficient of zeta 3 relative to pi cubed in this equation. And so when I see a sequence like that, and I can, using PSLQ algorithms, discover empirically what these are, I want to find it. And here's a solution for this integer sequence. You won't find this in the OES for a while, and so on and so forth. It corresponds to this number Gn, which is a product of things that involve Bernoulli numbers, and this number Bn, which is the Lucas number of a series in q of the square root of minus 15 in this combination. I think this satisfies an 8th order recurrence relation. And that's just telling me what the denominators in the formula for zeta of 2n plus 1 is. The numerators here involve this number Bn, and these numerators down here I know for all n, and this amazing explicit expression. And then finally, there's this, and these I can prove using the easy terms in Ramanujan's things. All of those rational numbers come from here, yeah? But I can find exactly what the rational coefficient of pi to the 15 is if I bookkeep all those very large number of finite sums of products of Bernoulli numbers, and I calculated what this rational number was for zeta of 2071 or something like that, and it's divisible by a 6,000-digit prime. So that's just a little game to play. Now, yeah, still on time. Now I tell you this game of target golf that I've evaluated, that I've invented for myself, just to keep me intellectually alive in my retirement. See, I've called attention to a preprint down here. In December of last year, Simon Plouffe, who likes to use empirical mathematics, sent me 3 formulas better than Ramanujan, right? And I had not seen these before, and they'd not been published before. So he empirically outperformed Ramanujan. The first thing that I did was to see if I could use my Feynman diagram to do it, and I did that. But we're now up to version 4, because I put out a version in January, all of which is correct, but then I found even more ways in February, and even more ways in March, and even more ways in April, and I hope I'm finished now, because I think I've invented a game of golf that only has 8 holes, that only has 20 holes. And here's the game of golf. I've found, using complex multiplication with these fundamental discriminants, here Ramanujan used d equals minus 4 to get Gaussian integers. Here I've used d equals minus 15. I say the order of merit is e to the, if the asymptotic ratio is e to the minus pi of pi times square root of a. So Ramanujan's got e to the minus 2 pi. He's at a equals 4. And you see 400 over 99 is slightly better. And this is really spectacularly better. This is like, it means it's converging twice as fast because we've gone up from 4 to 16. And how on earth did I prove these? Well, I did it because I know that the expansion of a Lambert series is in terms of polylogarithms. Now, most mathematicians, well, they can see that, but they don't see how it's useful. But here it's extremely useful because if I translate this into the z-plane, it means that if I multiply q by roots of unity modulo a prime, I end up with something simple. This would be, for the gamma function, called the multiplication formula. But if you work out what actually happens for these Lambert series, you could say, well, I've evaluated it p of z over half, or p of z plus 2/5, z plus 1/5, z plus 0, and that will be at 5z. You get a term at 25z as well. Now, this is true for all the primes. I can then, from it, derive much more complicated expressions just where I sum over groups of units modulo a composite value of n. I don't know. I don't need to know that, right? Because this is the only... Yeah, but it just comes from the elementary expansion. Expand that in terms of that. You're taking sums of polylogarithms, which is apparently nothing to do with modular forms, right? Polylogarithms of roots of unity, right? Yeah. So we know how to take logarithms over roots of unity, modulo prime, so we know how to do it. And when you do that, you separate out terms, you find something that involves p squared. Now, you can go back to saying, well, this is related to modularity. But for me, you know, I want a formula that I can show Euler, and he says, you know, trivially obvious. You don't need to know who heck he was to see that this is true, right? So now I can go to groups of units. Now, the formula for groups of units get more complicated, but these are the groups of units that I use, and they're groups of units that are small. So phi of n is quite small. And this corresponds to a game of what I call target golf. So here's the game. Here's the fundamental domain. Okay. You line, here's origin. You want to get up here to large imaginary z, where you're going to outperform Ramanujan. Ramanujan sits here and says, I transform myself to myself. And so I'm equal to some combination of pi cubed and down here. But we start off with lots of, on a target range, with lots of golf balls lined up outside the fundamental domain, right, down here, with a common value of the imaginary part of z, which I haven't revealed, which would be some algebraic number or whatever it is. And then and our aim is, can we use modularity and periodicity, quasi-modularity and periodicity, to end up all of our golf balls on the imaginary axis in the fundamental domain, all of them beating Ramanujan. If we can, you see, we've started off with something on the right-hand side, it's purely on the imaginary axis. If I was here, then I can shoot myself up to here. Of course, that's no good, because all that does, it tells me that pi cubed and zeta 3 is relating to something that converges fast and something that converges slowly. But here I take lots of things that converge slowly that add up to something that converges fast. And so it's this target golf, and I assert that this golf course has at least 20 holes that you can play with these discriminants and these groups of units, and from massive integer relation searches suggest that there might be no more than 20 ways of doing this. Certainly there's a finite number. So just out of the sheer joy of exploring in Ramanujan's footsteps, I suggest that there are precisely 20 ways of outperforming Ramanujan with quasi-modularity and complex multiplication. And they're on time, I think. Thank you for your attention.
So here you expanded the Lambert series in LIKs, which are the F1 polylogarithms. Do you know of examples where a series of F2 higher polylogarithms?
No. But that's a very obvious question for me to ask. No, in a way, you see, I've made this talk as absolutely as classical as possible. I've tried to write it in a way that has the minimal amount of provable mathematics in it. Right? Because Ramanujan discovered these things without benefit of learning, in a way, right? And Bruce spent a lifetime trying to prove some of them. You get a T-shirt from Bruce for proving something from Ramanujan notebooks. I have a co-author, David Bradley, whose proudest boast is that he has 2 T-shirts for proving Ramanujan. Well, here now is how to prove Ramanujan. No, I haven't showed you how to prove Ramanujan. You use contour integration, essentially, Grossfeld showed. But here's a way of proving all of the things which, it took 15 years to prove that the left and right-hand side of my equations were related by unity, and now it's 3 lines of computer algebra using quasi-modularity, and I've never seen it spelled out this way. I mean, maybe you take it for granted, but what I'm doing is essentially using quasi-modularity at what did I say? Yeah, at weight minus 2000.
What changes the for loop?
The for loop really is a Calabi-Yau threefold, and there's no modular parameterization of it. So what you do is you define it from the structure of the denominator. You can evaluate the L function at the primes, and then you assume that it's a function that you're dealing with the L value of an automorphic form with a particular character associated with it. It will be Q. It will be Kronecker Q at 15 in the case I was doing, and then you need to find the contribution of the prime at infinity. And the Feynman diagram is one of the L values of this. And it's very easy for people to study the discontinuity of this diagram, which satisfies the homogeneous 4th order differential equation. And they can write beautiful papers about that. But of course, the most difficult thing for them to do is to find the solution of the inhomogeneous equation. And the people that have been doing that recently at Bonn very well Albrecht Clem, but also very brilliant master students of him called Kilian Bernach, who use modularity to clean up on that, and also to obtain the areas of black holes from compactification of type 2a supergravity onto a classical black hole background. I was always told that compactification led to infinite numbers of degrees of freedom, but if you want to do it on a black hole background, you only end up with 2 possible areas for the black hole, and they correspond to modular forms with particular particular levels. If you're interested, in my 22 root result, I had an emergency slide down here. What you do to find the L values, here's now an L value that you get. I think you can see that this has got 6 special functions in it down here. It corresponds to the value of a 1-by-1 matrix. So I take these integrals. This is the number of internal propagators. The number of I zeros is the number of ones that are on shell, either because external particles or I've cut the line, and the powers of X correspond to putting blobs on the line. So you make matrices out of these Feynman diagrams, and the determinants of these matrices are the critical L values inside the critical strips of things with well-defined properties at the primes and down forth. And we claim that this is the biggest prime ever found in the Langlands program. Langlands program says that this determinant ought to be, taking out the power of pi to the 30, ought to be a rational multiple of this critical L value. And there are primes down here, and we're calculating, this is a modular form, the degree of the equation down here is 20, and you need huge calculations to get up to primes, value primes of 10 digits even to begin to approach this. And we cleaned up with all sorts of other things, and here's now a conjectural value, because we only could get after, I think there are 30 gigahertz years of computing to obtain 14 digits of this L value, and you see 14 digits it's not quite enough to convince yourself. So I offer that as an example of how automorphic forms, right, continue all the way up there. I can't hear that. You say it more clearly, please, Grigi. Yes. Yeah, well, it starts off, if you're putting in this matrix, in the top left-hand corner, you're putting the Feynman diagram. And then you're putting in things with more suppressions at x equals 0, that way. And as you go down, you're putting in things with less suppression at x equals infinity. And it's the determinant of all of them. So I don't know how to use a saddle point approximation for that. For any particular one, I could match the small and x behavior. But, you know, and this determinant I've got, I don't take everything. I only take alternate rows and alternate columns, because that's what the Grothendieck disciples tell me to take. Anyway, it's just a bit of pure mathematics beside that. But I'm rather proud of this, because, you know, normally when you say, is this true up to a rational number, the number is normally something like 1/6. In this particular case, it's got a telephone number in the Langlands program. Yes. Well, he was interested. But there were no tricks. Don is very good at tricks. You go to Don where you want to do something, and he finds a way of doing it. We'd done it, right? So, but Kilian Bernish had a beautiful result. He went to Don and said, I'm interested in something that's not a Cuss form. It's the thing that I integrate to obtain the quasi-periods of the modular form, and it's got a very nasty Laurent expansion in 1 upon Q before it goes down here. And I want to classify the space of such modular functions, and there's no way of doing it. And Don said, well, you've got a weight 8 function. Perhaps it's a weight 4 function. Perhaps it's a weight 8 Cuss form multiplied by some modular function that's singular in Q. And it turned out that it was, and the dimensionality of the space of cusp forms at weight 8 that answered this singular problem at weight 4 was only 30-dimensional. And so Gillian could then calculate, it's complex valued as well, calculate 32 complex numbers in the Q expansion to determine which it was, and then integrate it exactly. At the end of the day, all he got was the Bessel integral, which I already had to 1,000 decimal places, but he found the modular value of that. Now that's the sort of problem you take to Don, you see, because that's just sheer cunning and intuition. Solve a problem. Yeah, well, I think I should show you the paper. So I know what their functional equation is, right? And so there's a general program. It was written by Tim Dockschitzer, right? That if you know the modular equation, you know the conductor, and you know the values at the primes and how to compute it, then it will compute for you the value of the L function any way you like. This is now implemented by Henri Cohen in Paris, but when I was doing it, and so on and so forth. So there's a very well thing. It's turning, and so the local information at the primes just comes from counting zeros of varieties. I mean, there are better ways of doing that, but that's how initially these modular forms were discovered. People just said, look at that variety in X, Y, and Z, count its zeros modulo the prime, in f of p, modulo p, and then look for a modular form whose Q series has Fourier coefficients equal to that modulo p. And that's how they guess the modular forms. So,
Can't you use some exact results from the Sine-Gordon theory or the Bullock dot theory? Because on those integrable models, we know exactly the mass gap relation. And all your diagrams appear on those theories.
So we're talking on the right. I mean, this is a massive theory already.
Yes.
So, but
I mean, you take the Sine-Gordon Lagrangian, it's integrable. You can think of as a perturbation of a massive boson. So when you calculate the mass of that particle, then you encounter very similar diagrams.
you encounter very similar diagrams, but is there a common mass put in them? That's the thing, because the generic situation in which you'd have any mixture of masses, I mean, looking at what are called the equal mass bananas, would you have the same mass on each of your internal lines?
Yeah.
Okay, well then I should very much look at it. Thank you.
Also, I have a question concerning the first part.
Mm-hmm.
So you analyzed the 6-dimensional 5 to the 3 shape.
Yes.
You calculated this anomalous dimension, and you considered only a subset.
Yeah,
of
absolutely,
dimension.
absolutely. Tiny subset.
What about the relation to the real result?
Very, very tenuous. The next step, first of all, notice just how I mean, thank you for pointing out how delinquent and bankrupt this calculation is. Notice I've got no diagrams like that. I've got no vertex renormalization, yeah? And notice that I've only decorated one line, right? What I should really, if it was phi cube theory, I should really be looking at is sigma is equal to pi in there, whereas pi is equal to 1 over 1 minus sigma. But that's too difficult for me to solve, right? I don't know any differential equation for that. I can analyze it order by order in perturbation theory. So the person that looked at this is Marc Bellon. And first of all, you know, it's not a green function, it's just something intermediate. So all I'm doing is, I mean, the whole point of this exercise was to show how the iterated subtraction of subdivergences is automated by the Kohn-Kreimer Hopf algebra of renormalization. And this is the Hopf algebra of undecorated rooted trees. You see, this is a tree. There's the root. That's the family tree. This is a rather trivial family tree. There's just one successor down here. This is a rooted tree with 3 children down here. And so the number of Feynman diagrams that I've got is increasing, but not factorially. it's increasing in a power way given by the Otter constants of enumeration of rooted. So there's no, now you had to be careful with nomenclature. In the physics, there's no instanton. The instanton is associated with the factorial growth of a number of Feynman diagrams. So here I'm dealing with something that only has a renormalon that comes from these chains. And I've got renormalons inside rainbows and rainbows inside renormalons, which makes it an interesting mathematical question. But this tells me nothing about the real world. The important thing was to do it in a renormalizable, in a just renormalizable quantum field theory, which is why we did it first for Yukawa theory, which Gerald and Michael took up, and then for phi cubed in 6 dimensions. It's completely useless calculation. It's just fun to do.
One interesting thing is if you take the chain target, you can use this as an example for another.
Yeah,
You get 3 graph paths.
I've showed you.
But you include these other diagrams and you get
Yeah, so what Gerald is saying is what I pointed out down here. That is the exact answer. And the video said take partial fractions, which is the obvious thing to do, but I prefer to do it down here. It's just 3 poles in the Borel thing, and equally spaced. But people don't even know how to do this, or at least Volodya Smirnov and Martin Benecke promised they would try and look at 2 renormalon chains. But already this becomes difficult. I mean, they were doing it in QCD, and they were doing it for deep and lasting electron scattering. But if you have a graduate student that might fancy a bit of a challenge, see how much progress they could make with putting any number of bubbles on both lines. Thank you.